Yeah, so the next speaker is not Michael Scherer, but we found 3 replacements for him. So we have a couple of shorter talks in this afternoon session and then a longer talk afterwards. So the first speaker is Shoja Ray, and his talk was already announced on quantum critical behavior of the cross-level SO3 universality class. So please, Shoja.
Yeah. Can everyone hear me?
Yes, we do.
Thanks for the kind introduction, and thanks to the organizers as well for what has already been a very instructive and enjoyable workshop, and also for this unique opportunity to present my work. And when I say my work, obviously I mean our work, spanning 3 cities and 2 countries. So without further ado, the first question you might ask yourself when you see the title is obviously why one would want to look into yet another variant of the Gaussian universality class, having already been studied in quite some detail in the context of graphene, for instance. And for that, I have to take you back. I'd like to go 1 step back and look at the microscopic motivation. And Lucas Janssen, in his talk just before the poster session, already mentioned that you have this kind of spin-orbital liquids that are possible, which is kind of a generalization of the type spin liquid, where you add, is my mouse pointer visible? Is my cursor visible?
Yes, I can see it.
Excellent. So you tack on to the original spin degrees of freedom, some orbital degrees of freedom, and what you always have with these type-like liquids is that rather than spin degrees of freedom, if you spin degrees of freedom being the elementary excitations, you have fractionalization and you have fermionic excitations as the actual elementary excitations, the low energy excitations. So the low energy theory of this system is actually not one of spins, but actually one of fermions, which are called spinons. And so this model with just K, this leads to an with SO3 matrices. This leads to an SO3 spin liquid, and if you add this J term to it, you can see just by eye that that if J is large enough, this would actually favor a Néel-ordered phase, because this is just the standard exchange interaction, antiferromagnetic exchange interaction. And so the question is what happens in between the liquid, the spin orbital liquid and the Néel-ordered phase. And the answer to that is you get this new kind of universality class, this cross-level SO3 universality class. The star refers to the fact that we have spinons rather than actual electrons, which, however, will not be. I'll try to only make statements where this star doesn't really play an important role in this paper. So the spin orbital generalization was, you can read that up in the physical P rapid communication, and the follow-up PRL introduced this GN-SO3 universality class. So this is kind of the extrinsic motivation, the microscopic picture, but also from so this is the topic of the title. This is a topic that was mentioned in the title. So that was the microscopic picture, but also from a universal sort of perspective. This is an interesting version of the Gaussian universality class, because you have an SO3 flavor symmetry, and it's somewhat different because it has SO3, despite being a simple Lie group. So roughly speaking, all the flavors can talk to each other. This is not like a product of multiple Lie groups. It's really a simple Lie group, and in spite of all the fermion flavors being able to talk to each other, the symmetry breaking pattern is such that one flavor remains gapless afterwards. And so it's a novel universality class, unlike the Z2 or the Heisenberg universality class. So unlike the chiral Ising or the chiral Heisenberg universality class known from the graphene context, and also so we're studying in its own right, and also what's known about this so far was the first order corrections, quantum corrections in epsilon and 1 over n, which was introduced in the PRL, which was calculated in the PRL that introduced the cosmic Basel III universality class in the first place. And so that's sort of what was our motivation. So our motivation, and what I'll speak about in this talk, is our effort to come up with refined estimates by doing the epsilon and the 1 over n expansion to higher orders and perform an FRD calculation, and then try and come up with combined estimates. And so first, the idea of the epsilon expansion. Well, I don't really need to go into too much detail because Peter Marquardt had a much more detailed talk about the idea of the epsilon expansion. Essentially, for these relativistic universality classes near 4 dimensions, the cover and the self-coupling becomes marginal. So that's where perturbation theory is under control, and that's where I can do loop expansion. But ultimately, you need to set epsilon to 1, so higher loop corrections play an important role. And obviously, there's a combinatorially large number of diagrams and also more complicated topologies that turn up at higher and higher loop orders. And so you need to use several sophisticated tools to automatize the computation, because if you wanted to do it by hand, the computation time would probably exceed the lifetime of the universe. And so, yeah, so thankfully we didn't have to reinvent or invent the wheel, as it were, in this case. And there's already quite a sophisticated framework in place, which we were able to use. So the large N expansion is based on a complementary but still quasi-perturbative idea, where if you send the number of fermion flavors to infinity, it roughly corresponds to mean field theory, and then you can compute systematic corrections in 1 over n, and you can and if you do a resummation, if you reorganize the perturbation theory this way, it turns out that you have to solve Dyson-Springer equations consistently, which can be done order by order in 1 over n. And John Gracie is, of course, a big name in that business. So it's yeah, not a coincidence that his name appears here. And so that's the idea behind the 1 over n expansion, which we performed to 1 over n squared, to order 1 over n squared. And the final idea is the functional renormalization group again. So this one is sort of truly complementary if you really go take the Wettrich equation, which is a pretty beautiful equation because it's one loop exact, and solve it really self-consistently. Then you get really non-perturbative and results which are truly complementary to the other two perturbative approximations that I told you about, or quasi-perturbative approximations that I told you about the last couple of slides. And obviously, this equation is exact, but not exactly solvable in general. So you have to do as kind of approximation, and in this case, you could call it, well, something like a 0th order derivative expansion plus wave function renormalization. So in addition to the fact that you use the full non-perturbative propagator, at least within the realm of your self-consistent ansatz for the effective action. You also include arbitrary orders of botonic self-couplings, all the way up to potentially infinite order. Okay, so this was those were the methods, but how do you get to the final numbers from there, and how do we estimate errors? So in the case of the series expansions, these are typically only asymptotic with convergence radius that is of the order of 0, not even 10 to the 0, but just 0. And so it means that you typically have to do some kind of extrapolation. And in this case, we just used part2 approximants. And in this case, so this is, for instance, the epsilon expansion, the series expansion, and epsilon equals 1 is where we want to get to. And then depending on, I guess, luck, because there's really no real way to see which one of them will be good or bad. Often part2 approximants can have poles, in which case they're not useful for extrapolating to epsilon equals 1. And there are others that are not that are, so those that do not have any poles, they are good, and those can be used to give a final get your final estimate. So you can see here that you have a kind of window or kind of band, which is what the epsilon expansion would seem to suggest for this particular critical exponent. And for the 1/n expansion, you have to think of like a perpendicular axis to the epsilon axis. Again, 1/n, you'd start with 1/n equals 0, which is n equals infinity, and then descend to 1/n equals 1/3 in our conventions. And in this particular case, we only have one good extrapolation. That's a bit unfortunate to hear. You can't really find, you can't really make too rigorous the error estimate, which is in any case a bit optimistic, but in this case it's a bit extreme. And in the case of the functional renormalization group, it's not easy to do an extrapolation analysis. So the functional, so at least the LPA prime, if you want to embed it into a larger framework, it would be the derivative expansion. So this would live in a third direction, that is, which is, I guess, the order of the derivative expansion, and that one. And again, to go to higher orders of derivative expansion would be too much work. So what you do in this case is to use the regulator dependence as a proxy for the error estimate. And so quickly in layman terms, any path integral needs regularization, and the regulator, the shape of the regulator is the way the regularization dependence can turn up in FRG calculations, and in this particular case, so typically you'd expect the regularization dependence to drop out in physical data like critical exponents, but in non-perturbative approximations it might not, and this is what is used as a way to estimate the error, which again can be optimistic in certain cases. But so this is what we have, and then you average over the methods. I guess this is too technical, and in the interest of time, I'll skip this. I'll just flash this slide for half a minute to say that we put some brain power into it to come up with the final numbers. But these are the final numbers that we come up with, and so what can you make out of these final numbers? And one such thing which and one such idea would be to, for instance, use these as kind of a diagnostic tool. So quantum spin liquids are very difficult to diagnose because they are characterized simply by the fact that they do not order at low temperatures in some sense. And obviously, the absence of proof of order is not proof of absence of order. And one such thing you could do with critical exponents, a game you could play, at least as a Gedanken experiment, is you could look at SU2, like you could think of like this 3 fermion flavors to 1 gapless and 2 gapped fermion flavor symmetry breaking pattern. You could also get this where you just have an SU2 symmetry breaking, and what remains, and there's a spectator degree of freedom, which could, for instance, live on the Andromeda galaxy for all you care. And this degree of freedom does not go spontaneous symmetry breaking. Can you distinguish them? And for this particular case, we have very good numbers from Lang and Leichli. Thomas Lang is the audience, I think, or at least participating in this conference. And so for this, we have numbers with very good certainty estimates. But in this in the above scenario, where all flavors can talk to each other, we have a different number. And obviously, this 0.07 uncertainty is quite high, but that's something one can work to improve on. But essentially, there is a way to distinguish this via critical exponents. And again, spin liquids, it's easier to destabilize a spin liquid than actually measure a spin liquid in some sense. So that's something that may be useful even experimentally for the future. So to summarize, I'd say the error bars are not small, but you could say that we are more confident than if these error bars were just internal error estimates or optimistic internal error estimates from just one method, but like we have multiple different methods with different regimes of validity, with complementary regimes of validity, and it can then be a point of reference for future efforts. And obviously, one thing that I sort of glossed over, there is a tension between the internal and external errors. And that is something that one could look into in more detail by going to higher orders, for instance, which would make the internal errors more, the estimate of the internal errors more reliable, and also maybe, I mean, there could also be some truly non-perturbative stuff going on, which would make which would mean that this tension will never go away. But yeah, that's something that can be looked into in the future. And for further details and results, the PRB published this year. And I'd like to close by thanking my collaborators, the Bernhard Erich, Daniel Kuti, and Michael Scherer from Köln, John Gracie, who was an organizer of this conference, from Liverpool, and Lukas Janssen, and especially Lukas Janssen, who is my PhD supervisor as well, from Dresden. And finally, I'd like to thank you, the audience, for listening, and I'm open for questions.
Thank you, Georgia. Thank you very much for this integrative talk as far as methods are concerned. So we have time for some questions. Questions? So then maybe I have one. So you have these 3 different methods, and of course you showed this nice workflow where we kind of try to get to an agreement. But I guess that involved some amount of weighting the different procedures. So weighing, putting weights to different methods. Could you say something more about this?
Yeah, so weighting is something that we did think about, but ultimately decided not to do, because it's so sometimes you just, like in this case of the 1/n expansion, where just randomly only one Parity approximant survives the niceness criteria. You don't have an internal notion of error. And also, for instance, in the FRG calculation, if you can see here, you would typically take the regulator dependence, but the linear and sharp cutoffs just happen to, I guess, agree very well in this case. So that's something that may or may not survive higher orders of derivative expansion, for instance. So ultimately, we just did an unweighted average over the methods. Yeah, so if you go to higher orders, then I guess everywhere you would end up with errors, and then you could maybe think about weighting by the individual errors, for instance. But in this case, it's just very hard to say which method is actually better. So I guess you need this. All methods really are equal, and none of them are more equal than the other, and we need this equal weightage at this level of the calculation, at least.
But the substantial internal consistency, that's very good, very nice result. Joseph.
Yeah, I had a question about the large N expansion. So here, N is the number of, what is N here, actually?
So N equals 3 is what we have. I guess that's the best way of fixing.
Yeah, I guess my question is that, so if you look at your Lagrangian, right? So your fermion flavor I ranges over some range, and then A goes over some range. Yeah, but I guess if T is an SON matrix in general, then A would go, if A goes from 1 to N, then I would go from 1 to N minus 1 over 2, right? So the number of fermion flavors grows quadratically at large N. So that changes the scaling for the counting.
We're not going, so this N really, so we are really looking at SO3, and so the SO3 always remains SO3.
Okay.
This realization, and then I is just a number. So yeah, I, and then you have just more and more copies of the SO3.
Okay, so you don't have an SON symmetry at large N.
No.
Okay.
That would that's a different generalization which one could also look at, but yeah.
Okay, so it's like SO3 to the nth power. That's your symmetry, basically.
You could, yes, you could say that. Yeah.
Okay, thanks.
Okay, I think we need to move on to the next speaker. Thank you, Shoja. Thanks. And the next speaker is Johan Ostmeyer. Johan, are you around?
Yep, I'm here. So you should see my presentation now also.
Yes, we can see it perfectly. Thank you. So next talk by Johan Ostmeyer on simulations in a Hubbard model with tensor networks.
Yeah, thanks for this great opportunity to present our recent preprint. Actually, I've been announced with a different topic, namely concerning the quantum phase transition of the Hubbard model. And then I thought we have already seen this nice talks by Sandro Sorella and Fakar Assad on this topic. So I will glance over that very briefly and then dive into a different approach, which Manuel Schneider, myself, Karl Janssen, Tom Lu, and Carsten Obach recently put on the archive. Yeah, so as we have seen in several talks before, I'm concerned with the Hubbard model, with pure on-site interaction, and also focusing on the honeycomb lattice. And recently we did quite similar work to what Sandro and Fakar showed, extracting different observables with hybrid Monte Carlo simulations actually on pretty large lattices, including 102 by 102 unit cells. And we did some thorough thermodynamic limit and continuous time extrapolations, compared different observables, and confirmed what we already heard on Monday once more, that the phase transition we get in that model is one from a semi-metal to an insulator simultaneously to an antiferromagnetic order emerging. And that is more or less everything I want to say to this quantum phase transition. If you have any additional questions, you can visit my poster. The question I want to address now is what to do beyond this original problem if we want to go away from half filling. And yeah, as probably most of you know, away from half filling, for example, with a finite chemical potential, the Monte Carlo simulations encounter a sign problem, which can be alleviated by different approaches. So the easiest one is so-called reweighting, where the complex phase is simply pulled into the observable, but this only works out for a very moderate sign problem. And a more sophisticated approach, which has been investigated very thoroughly in the recent past, is using holomorphic flow to approach Lefschetz thimbles. Lefschetz thimbles are manifolds in the complex plane where the sign problem goes away. And if you deform your integration contour smoothly, then you can actually integrate along these thimbles without any sign problem, but finding these thimbles turns out to be not an easy problem. And that is why we recently focused on a completely different approach, namely using tensor networks. And now I'm going to give you a brief introduction what these tensor networks actually are. We use a very specific species of tensor networks, namely the so-called projected entangled pair states, which use the idea that if you have a mixed state with some degrees of freedom that are coupled via tensor products, and you have some coefficient with a lot of different indices, then you can split this coefficient tensor into a product of many smaller tensors that are contracted by some auxiliary indices. So all of these indices that appear twice are contracted. And the idea is now that these tensors that you generate can all be truncated in these internal indices to some finite dimension, so that instead of using the original exponential size tensor, you can actually use a linear number of truncated, that is, some polynomial size tensors. And there is a very nice scheme to visualize these tensors. In our honeycomb lattice, we would get structures that look something like that. Every blob here characterizes one tensor, and every solid line corresponds to one internal index alpha, and these dashed lines correspond in our notation to the physical index, which I denoted S here. There are a lot of slightly deviating schemes that you find in literature. We stick consistently to denoting the physical indices differently from the internal indices so as to not get confused, but this is not necessarily the case. So sometimes you have to watch out for these subtleties. So in principle, these tensor network approaches were out there for a long time, and a lot of different algorithms have emerged in the last few years, but most of them focus on bosonic tensor networks, and this has a very good reason. Fermionic PEPs have the problem that crossings between lines are not trivial, and this is simply coming from the anti-commutation of the fermionic operators. So two creation operators anti-commute, and this means essentially in our tensor network language that the crossing of two lines is not the same as if we just pulled them apart. And in addition, it's also not just the negative version, because if you, for example, commute two different annihilation operators with one other operator, then you don't get a sign. So what you have to do is to introduce a so-called swap gate, which we denote by these diamonds. And it is a matrix that can be multiplied to the tensor here element-wise, which contains 4 blocks. And for this even number of creation or annihilation operators parts, you have a positive sign, and only in the case that you compute 2 odd numbers of annihilation operators, you get a negative contribution. With these swap gates now, we can really encode all these different crossings that we encounter in the PEPs. And there's one additional subtlety, because the tensor network is, as any calculation with the Hubbard model should be, parity conserving, which means that an even number of electrons will not cross over to an odd number of electrons. And we have to encode them by an additional degree of freedom, which we denote by this parity link that we add to one and only one tensor of the network. And this parity link can then come with an odd and an even parity, so that we have 2 different subspaces that are distinguished only by the parity index here. And these subspaces are not only orthogonal, there's also no way one vector from one of the subspaces could communicate to another to a vector of the other subspace. And this now allows us to fix the subspace by choosing this parity link. So instead of choosing it 2-dimensional to simulate really the complete space, we can fix it to even or odd parity and simulate the 2 subspaces independently. This now has the great advantage that, for example, if we are doing a ground state search, we can find not only the global ground state, but also the ground state of the opposite parity sector. And so how do we do that? For a ground state search, we first have to fix this bond dimension that gives us the truncation of the system. We somehow initialize our PEPs with random numbers, and then we perform an imaginary time evolution with a Trotter decomposed evolution operator. We can do this completely locally, which is simply due to the fact that the Hubbard model has only nearest neighbor hopping in our formulation and on-site interaction. So you have at most 2 tensors involved in any operation. And in the end, to get expectation values from our ground state results, we have to contract the complete network once. The emphasis here is on once, because the time evolution itself, so the ground state surge, does, at least at this level, not involve contractions of the complete network. It's completely locally, and that's very efficient. So yeah, these local updates in the tensor network slang, they're called simple updates, where we just apply the trotterized imaginary time evolution operator to 2 of the tensors. That means that we contract over the physical indices here. And this picture actually can be read like a vector matrix multiplication, where in the end we get some object that has a higher bond dimension here than we would allow a priori. So we truncate back again. This can be done very efficiently by a singular value decomposition. Now we have all the building blocks we need, and we can actually look at some results of simulations. First of all, I want to address the question that we had originally about this sign problem. So what if we introduce a finite chemical potential, go away from half filling? And the answer is the tensor networks just don't care at all. We can simply do the optimization in the even parity sector and the odd parity sector, and the chemical potential is just one parameter that influences the values, of course, but it, at least in first approximation, doesn't influence the quality of the convergence. And what you see here is for the even parity sector once and for the odd parity sector, for 12-side lattice, so that is the largest one where we could do an exact diagonalization of the ground state to really compare with exact results. You see the exact values of the energy at different chemical potential, and you see the tensor network approximations for different bond dimensions. And there is, in pretty much all the cases, a very neat convergence, where with bond dimension in the region of 20, the convergence is already far below the percentage level. And these tensor network simulations, in fact, were very significantly faster than the exact diagonalization, at least in our implementation. Also, we did some comparisons to Monte Carlo simulations of this system. So it's at finite coupling and finite chemical potential, and it turned out that this sign problem was just untreatable with Monte Carlo simulations.
Johan, you have 2 + 3 minutes.
2 + 3, perfect. All right. As I already said, we can do these 2 parity sectors independently. And this means that the difference between them directly gives us the single particle excitation gap, which again works out very neatly. And this is an order parameter of semi-metal mod insulator transition, which of course is a nice thing to reuse. We also can scale up to pretty large lattices. We nearly have linear scaling. And this means that at finite coupling, comparably large lattices, so 15 by 15 unit cells and finite chemical potentials, we produced the first simulations at least that we are aware of with these systems. And then obviously the question remains, did we solve it? Did we violate the no free lunch theorem? And the answer is no, sadly not. There are still problems. The odd parity sector simulation is not always stable. In particular, when we have a strong coupling that is a large gap, we sometimes jump down to the even parity sector, which is quite sad because then we can't extract the gap anymore. The even parity sector simulations turn out to be very stable in all the simulations we tried up to now. We thought about possible solutions, which include, very unfortunately, non-local full update, which obviously is much slower. Alternatively, we could just stick to the even parity ground state, use different observables, so not the single particle gap, but something else like magnetization, susceptibility. We are still thinking along these lines. And also, we are open for suggestions. If you know how to fix our jumping problem, please tell me. Yeah, let me very quickly summarize. We used these PEPs, so projected entanglement pair states, to approximate our network of honeycomb lattice where we applied the Hubbard model. We could, with this approximation, simulate with decently high accuracy at finite coupling and finite chemical potential. And we still have several problems to fix, the most important one being this jump from the odd parity sector to the even parity sector. And with that, I am open for any questions or suggestions.
Yeah, thank you very much for the talk, for exchanging the topic in the very last minute and telling us about the tensor networks. Other questions? Yeah, okay.
Yeah. So can you measure something else than the energy? For example, you know.
Yeah. So we can pretty much without any additional effort measure any local operator, which means magnetization, particle number.
So magnetization will be hard because it should be always zero, right? If you don't break the symmetry, but the particle, can you calculate the particle number versus the chemical potential, for example?
Yes, we can do that.
And so do you know how it, I mean, that's already a very interesting quantity to look at. Do you?
Yeah, we actually did that. I don't think that I have the results flying around here, but for this simulation where at zero coupling we know the exact analytic solution from exact diagonalization, we pretty much see a similar convergence in the particle number. So it's not on point for finite bond dimension, but it's converging.
Thank you.
There's a question by Rajamani.
Hi, this is a question generally on tensor networks. I don't understand what the effect of this truncation is. Could you explain? I know why you have to do it because you want to keep it finite, but I don't understand what the actual effect of that is.
Okay, so I'm not totally sure if I get what you mean by effect, but obviously the reason is that we don't want an exponential size system. That's just obviously not tractable. The effects are that we just have a simulation, an approximation, sorry. And the approximation is in 1D very well classified. It is known that in 1D you get exponential convergence, and it is more or less postulated and sometimes observed that you should also get exponential convergence asymptotically in 2 dimensions, but as far as I know, there is no proof. And actually, this is also not what we observed. We observed more quadratic convergence, as you see here. So actually, we don't have a proof for this quadratic convergence either. It's just empirical evidence.
So the D is
the D is this bond dimension. So yeah, what we simply do is that we write a bunch of tensors where all these internal links that are contracted have dimension at most this cutoff dimension D.
So does the slope of that depend upon how close you are to the critical point in the theory?
Probably yes.
Okay.
But I can't give you a systematic analysis.
I think, Rajamani, people would generally believe this is essentially the analog of a real space RG transformation, this truncation effect. If that's any answer to what the physical underlying.
Be able to avoid critical slowing down.
I think it gets, depending on the algorithm, I think it gets harder near critical points. And there's a lot of literature about how to improve your algorithm to handle critical behavior. And so in that sense, critical slowing down comes back in that way. So the algorithms get much more complicated if you want to extract physics at the critical point. I only know it in the context of sort of space-time tensor networks. And certainly there, one thinks of it as an RG transformation, basically. So when one does this truncation, one does some sort of SVD decomposition and takes only the important singular values, which are meant to represent long-distance physics, roughly speaking, I think.
Yeah, what we observed is that near to phase transitions, but also anywhere where the ground state is degenerate or almost degenerate, you get severe stability problems and convergence slows down by a lot.
Isn't it also related to how much real space entanglement you can capture in the ground state wave function?
Yes, I think so.
Yeah, so it also crucially depends on the entanglement of the original physical function, yes.
Mm-hmm.
Yeah, so I see there's lots of things to be discussed on Gathertown, but I fear we have to move on to the next speaker. Yes, next speaker is Maxime Bishop. Are you around, Maxime?
Yes, I'm here. Should I start sharing the screen?
Yes, please.
Okay.
Yes.
Can you see my screen?
Perfectly, thank you. Yes, so the topic was already announced. It's on Fermi velocity renormalization. And yeah, so please start. Thank you.
Okay, so I would like to thank organizers for the opportunity to talk here. So I'm going to present results from our recent preprint on the Fermi velocity and renormalization from our large-scale QMC. And for the motivation, I'm going to go a little bit back to one of the initial reasons why graphene was interesting for high energy physics community. The reason was that if you look at graphene on substrate, then this substrate, it can actually change the effective coupling constant. And this effective coupling constant in graphene is large due to small Fermi velocity. And especially large is effective coupling constant in freestanding graphene, where there is no substrate, so that you have no additional screening of Coulomb interaction. And in this freestanding graphene, we have actually strong coupled quantum electrodynamics with alpha close, with fine structure constant alpha close to 2. And that's why this situation creates a kind of good playground to test our theoretical ideas on strongly coupled quantum field theories and strongly coupled QED in particular. And it was discussed that, for example, we can check Dyson argument on asymptotic behavior of perturbative expansion in QED. in normal QED, we can't really touch the start of asymptotic divergence, just because fine structure constant is small, so that we have really very good precision in our perturbation computations. But in this strongly coupled QED, we can probably catch this divergence much earlier, already at like first or second order of perturbation theory. Okay, yes. What observable can be discussed in this context? In principle, there should be something which can be observed in experiment, because what we are going to do is to compute observables from perturbative series, for example, and then compare with experiment. And when we start to diverge by adding more and more orders of perturbation theory, then basically it means that we already reached the point of asymptotic divergence of series. And one of effects which are actually observed in experiment was divergence of Fermi velocity when we approach a Dirac point. And here I just cite a couple of papers where this phenomenon was reported in freestanding graphene, but there were also some other experiments for graphene on substrate. Yeah, basically we can take this measurement and compare it with perturbative series. But the problem is that if you look at actual ways how it was done in experiment, then experimental data is subject for various corrections. For example, measurements were actually done at finite chemical potential, so that we can have additional screening of Coulomb interaction by finite density of charge carriers. Also, samples always can have some defects, strain, and so on and so forth. So that when we compare results with experiment, it's always very hard to distinguish. Do we have already discrepancy due to our deficiencies in perturbation theory, or it's just systematical corrections in experiment? And exactly for this reason, I'm going to introduce here quantum Monte Carlo. Quantum Monte Carlo can serve as an intermediate step between experiment and theory, because, as I said, direct comparison of experiment and perturbable series is complicated. Then we can do the same computation in QMC, and a comparison of QMC and experiment will serve as verification of our interacting tight binding Hamiltonian, which we use in QMC, and then comparison of QMC and perturbative series will actually be more clean and in some sense more better control. We can control all circumstances better than in actual comparison with experiment. Because in QMC, we of course do not have any lattice defects, we don't have additional screening of Coulomb interaction and so on. So we just do two comparisons. First is comparison, we do two comparisons. First is comparison of QMC and experiment, and the second is comparison of QMC and perturbative series. Which computations we picked up from theoretical side? We took just usual 2+1 QED. Well, it's actually not precisely 2+1 QED because fermions are in Flatland, but of course bosons can penetrate in whole 3+1 dimensions. And then we have this famous one loop result for Fermi velocity renormalization, which gives us logarithmic corrections. And then we also went to random phase approximation with dressed bosonic propagator. And actually in literature, there are also some results from two-loop RPA, but we did not go that far just because it appears that there are more important phenomena which makes this continuum perturbative theory not that useful, even at the level of random phase approximation, but I will discuss it further. So yeah, the questions to answer is, do we really get logarithm in QMC in an experiment, and how close can we, how good we are at predictions of this coefficient in front of logarithm. And then the second theoretical approach we pick for comparison is just lattice perturbation theory. As I will discuss later, there are various lattice scale corrections which were actually observed in QMC, and that's why we took lattice perturbation theory, which takes into account basically the whole microscopic physics of hexagonal lattice. And we also went up to RPA approximation, and also we did finite temperature lattice perturbation theory, because it appears that finite temperature corrections are important too. And setup for actual QMC, as Fahir already said in his talk today. We used special version of quantum Monte Carlo. We used so-called hybrid Monte Carlo for the reasons because this Fermi velocity renormalization is infrared effect. It is a divergence of Fermi velocity once we approach Dirac point. And that's why we need extremely large lattices to actually observe it in QMC. And in hybrid Monte Carlo, we can sometimes do simulations at very large lattices by make kind of trading of the stochastic representation of fermionic determinant for beta scaling. For example, here on the left, you can see the scaling of usual BSS QMC, and on the right, there is a scaling of HMC. So in HMC, you replace exact calculation of fermionic determinant by stochastic representation, so that you introduce additional fluctuations actually by the stochastic estimator for fermionic determinant, but the method has beta scaling. And in some situations, for larger lattices, we can actually win. And here on the left, you can just see this additional fluctuations introduced by stochastic estimator in HMC, so that it's actually huge additional fluctuations which we are dealing in HMC in comparison with BSS QMC. But still, with better scaling, in the end we win, and that's why for this particular situation, for very large lattices, HMC is a method of choice. Okay, let's move further, and can you see the next slide?
No, not yet.
Seems that computer is actually not working properly. I suspect it's the same problem.
Would you like me to kill the screen share and then you can restart?
Yes, I guess I should
okay.
disconnect and then connect again. So I'm very sorry for this.
He's back.
Okay, so yeah, I'm back. I'll try to.
Oh, hang on. Make you co-host.
Okay.
There, you should be fine now.
Okay, let me start it again. Okay, so can you see the screen? Yeah, I hope it will work now. Okay, so then what is set up for electron-electron interactions? We are going to check both effects of long-range interactions and short-range interactions, because here the peculiarity of this situation is that we have short-range coupling, which is responsible for this transition to antiferromagnetic mode insulator. And we have long-range interaction, which is responsible for Fermi velocity renormalization. But still, short-range interactions and lattice scale physics, despite being irrelevant at infrared fixed point, they still can influence some non-universal quantities, like, for example, cutoff we observe. And that's why, if you are interested in numerical comparison with experiment, we should check influence of these effects too. That's why we consider different setups for interactions with different Coulomb tail and different short-range interactions. And results. We look directly at dispersion relation in order to avoid difficulties with computation of Fermi velocity through finite step derivatives. And here you can see Monte Carlo results on 100 by 100 lattice and various fittings for them too. Results are for different strengths of Coulomb interaction. On the top left, it's a smaller Coulomb tail, and top right, it's larger Coulomb tail. And basically, all points except the first point are well fitted with logarithmic function, so that somehow we can at this point confirm that we indeed observe logarithmic divergence in QMC. The peculiarity is the first point. Why it is different? Analysis suggests that it cannot be finite size effects, because if we compare it with 48 by 48 lattice, then at 48 by 48 lattice is black points on top right plot. The first point do not actually jump upwards. But if we compare two different temperatures on 48 by 48 lattice, it's bottom left plot, then at smaller temperature on 2 times smaller lattice, we see the same jump upwards. So it's not surprising actually for Dirac fermions. We simultaneously scale temperature and lattice size, and we reproduce the same jump upwards from temperature corrections. And that's why we think that this jump upwards for the first point is actually finite temperature effect. And that's why, if we are going to fit this with logarithm and compare with experimental data, then actually first 2 points from Fermi velocity should be discarded. And here is comparison with experiment. We compare 2 setups for smaller and larger Coulomb tail. And for smaller Coulomb tail, extrapolation from QMC data, avoiding first points, actually shoots down a little bit below experimental data, which is not large surprise. And when we take CRP results with CRP electron-electron potentials, which should exactly reproduce suspended graphene, then extrapolation of QMC data exactly goes towards experimental results. That's why, at least up to now, at these lattice sizes, at this temperature, if you take into account that first points should be discarded due to finite temperature corrections, we can confirm that CRPA results, that CRPA potentials should actually reproduce suspended graphene even in strongly correlated regime. And now we can use it to compare with perturbative series and look at different effects which can influence the behavior of perturbative series. So here is comparison with lattice perturbation and Dirac perturbation theory. Again, for two different Coulomb tails. The main effects here are the following. First of all, if we take lattice perturbation theory in RPA and one loop setup, then we see that actually discrepancy is quite large, especially in cutoff. Because cutoff in lattice perturbation theory is not a free parameter, it is also produced by our perturbations. So that there is large discrepancy in cutoff and also discrepancy in coefficient in front of cutoff. It means that this is so strongly correlated theory that higher order corrections are important. With just one loop RPA, we cannot reproduce QMC at all. If you look at Dirac and Dirac system, it's violet line, and we use cutoff as just fitting parameter, then we see that actually Dirac theory does not reproduce neither QMC and neither lattice perturbation theory. So that there is discrepancy both in between of Dirac perturbative theories and QMC and continuum perturbation theory and lattice perturbation theory. Also interesting effect is that actually temperature corrections from finite temperature lattice perturbation theory are of different sign in comparison to QMC. In QMC, temperature corrections send dispersion direction upwards from logarithmic curve, while in lattice perturbation, temperature corrections, they always send dispersion relation down. So it is also a signal that higher order corrections are important in temperature effects.
Maxime,
yeah.
So we have -1 + 2 minutes.
Okay, I see. So basically, then I probably will skip this and just demonstrate the discrepancy between continuum and lattice perturbation theory. Basically, this discrepancy, which is evident here, at one loop level we have agreement, at RPA level we have discrepancy. And this discrepancy, it can be attributed to two distinct effects. It's effect of intervalley scattering. It can be understood from the analysis of polarization, and also its finite cutoff effect, because in real graphene we always have a cutoff. And actually, this can be understood both on analysis of polarization in lattice perturbation theory and in continuum theory too, if we just look at subleading terms in cutoff. And we tried to somehow save continuum theory, but it seems that it actually cannot be saved. We tried to add some additional terms in current to describe intervalley scattering, and we tried to add for fermion interaction to describe intervalley scattering, and also with all this stuff we could not really describe QMC results. And that's why we are going to these conclusions. That first of all, we have by our simulations, we have confirmed that CRPA potentials inserted in type binding Hamiltonian give good agreement with experiment. And by comparison with lattice perturbation theory, we conclude that higher order corrections beyond one loop RPA are important, so that we are really in some non-perturbative regime, and it is especially noticeable in high temperature corrections. And continuum perturbation theory in QED is really not that useful in quantitative comparison with experiment, because lattice scale physics, intra-valley scattering, and finite cutoff really influence coefficient in front of logarithm. So here is a summary of effects.
Yes,
thank
you. Hey, thank you. And there is a question by Oscar.
Hi, thank you for a very nice talk. I have actually a couple of questions. So first, you have a slide where you're comparing the experiment to your calculation. The experiment is done at finite density. I presume your calculation is not done at finite density, but you have a finite K. Do you just replace that K with KF?
Yes, yes. So this is pretty much we do what we do.
Okay.
Yeah.
And then the second question is, if you were to dial down the dielectric, dial up the dielectric constant so that the coefficient in front of the Coulomb went down, is there any regime where you start seeing the analytical calculations agreeing with your QMC?
Yes, yes, yes. I just did not add it in the slides, but you can see it in our preprint. Yes, we did this check, of course.
So very quickly, so for what value of alpha can you start trusting perturbation theory?
Okay, it's something around 10 to the minus 1.
So 0.1. Okay.
Yes, yes, yes.
Okay. Thank you.
Okay, and maybe a last question by Vladimir.
Can I?
We can't hear you.
Okay, so we see that these blue points on the experimental plots go down. So I wonder if you do lattice perturbation theory with finite chemical potential, would you observe the same effect somehow?
Well, yeah, this is actually an interesting question. This effect, I think, is screening of Coulomb interaction by finite chemical potential.
Yeah, yeah. So it should be reproducible within one loop of lattice perturbation theory, which
I can. Okay, short answer, probably yes. We didn't do that. We didn't do that, but probably yes.
It's interesting to check.
Yeah, yeah. That's actually a good note. Yeah.
Okay, I think we are already far behind schedule, so we need to move on. Thank you very much, Sim. And let's come to the next speaker, Peter and Roy. Peter, are you around?
Yep. Can you hear me?
Oh, yes.
Okay, good.
Can you share your screen, please?
Yep. Give me a second. So can you see my talk?
Can see, yes, now it's in full screen mode. Thank you.
Yeah.
Very good. So next speaker is Peter and Roy, and we'll hear about emergent SO5 symmetry once more.
Okay, so let me first take this opportunity to thank all four organizers for giving me this opportunity to present my recent work that will discuss the role and the signature of emergent symmetry on the global phase diagram of extended Hubbard model in monolayer graphene, which is a prototypical example of Dirac system in a flatland, on a flatland. So this work has been done with my current PhD student, Andras Sabo, and we expect this work to show up on arXiv pretty soon. So before we get started with the Hubbard model or graphene, let me actually take the opportunity to talk about symmetry and its importance and what aspect of symmetry will be required or I will be using for the remaining time of my talk. So it is needless to point out the importance of symmetry in physics, but couple of points I would like to make here. That first of all, we can divide this big landscape of symmetry, which has enriched our understanding of physics, into two broad sectors. One is exact and another one is emergent. So exact symmetry is the symmetry that is operative at any length scale or any energy scale. Like the time reversal symmetry is the ideal example, that either you have a time reversal symmetry or you don't have a time reversal symmetry. But on the other hand, I personally believe that the emergent symmetry is far more interesting than exact symmetry, without undermining the importance of exact symmetry. And emergent symmetry is a class of symmetry that cannot be observed at all length scale or all energy scale. It can only be observed over a certain range of energy or the length scale, such as Lorentz symmetry or chiral symmetry. So I will discuss some of them as we go along. And not only that, we can also divide the emergent symmetry into two sectors, that it is possible that the certain symmetries which is not present at all length scale can emerge at high energies, which we also call the ultraviolet energy scale, such as the seminal example will be the electroweak force or electroweak theory that unifies electromagnetic and weak forces, and the pertinent, the gauge symmetry is SU2 cross U1, and we get the concept of so-called the isospin doublet, and electrons and electron neutrinos, although their masses are not same, but when you look at very high energy scale, which is of the order of 246 giga electron volt, we can really forget about the mass difference between electron and electron neutrinos and claim that they are isospin partners. So this is one example where symmetry that was not present at the low energy but emerged at a very high energy or the ultraviolet scale. But I'm a condensed matter physicist. What is more interesting to me or more pertinent to me is the notion of emergent symmetry at low energies or at the infrared scale. So I will pick actually my favorite example, but the point is that there are many examples of emergent symmetries at low energy or at the infrared scale. So the examples that I will talk about very briefly to introduce the notion of emergent symmetry at infrared scale is the topological phase transition, specifically in 3 spatial dimensions. And we will see that this simple example will allow us to understand or appreciate emergent U1 chiral symmetry. So the system is the following, which I'm sure that the audience, they are very familiar with, is the Hamiltonian that is described by this massive Dirac Hamiltonian. The first term you can see, this is the standard Dirac kinetic energy. And the second term is the so-called the conventional or the regular Dirac mass that does not break any microscopic symmetry, such as parity or time reversal. Typically in high energy or even 15-20 years back in condensed matter physics, we used to undermine the role of these higher gradient terms, and we attributed all the importance to the low energy sector. But what we realized that in order to appreciate topology, it is also important not only we look into the infrared, but we also give equal importance to the ultraviolet part of the spectrum, which is captured by this higher gradient term, which emerges from, which results from Wilson-Dirac mass. This is this BK squared term. So the phase diagram of this simple Hamiltonian is also very simple, that if we take this coefficient of the higher gradient term B to be bigger than 0, then in the M bigger than 0 regime, we find topological insulator, which supports gapless surface states or H state if you are in 2 dimension. Whereas in the M less than 0 regime, you find a normal or the trivial insulator. And in between these two topologically distinct phases, you find a quantum critical point, and the universality class of this quantum critical point or the quantum phase transition between normal and topological insulator is governed by so-called the massless Dirac fermion. But if we look into the Hamiltonian or the corresponding imaginary time action, what we realize that when we are in the massless limit, then the action enjoys a global E1 chiral rotation by this famous gamma 5 matrix. But as soon as we have this uniform mass or the momentum dependent mass, which does not break any discrete or any microscopic symmetry, this chiral symmetry is broken. But what we will realize that as we approach this quantum critical point or this topological quantum critical point, this chiral symmetry we recover as an emergent symmetry. So what we do that we cast this topological phase transition in the renormalization group language. Then we can write down the flow equation for all three parameters, like Fermi velocity, which is a marginal quantity, Dirac mass, which is a relevant parameter that controls the transition between topological and normal insulator, and the coefficient of the higher gradient term, which is an irrelevant quantity. And here L is the logarithm of the renormalization group time. In terms of physical degrees of physical language, what this L means that how many degrees of freedom you have integrated out in the process of the coarse graining. So as L gets larger and larger, you are sliding down toward this so-called the Dirac point of the theory. Now you can take this coupled simple flow equation and find that the topological quantum critical point is indeed located as mass is equal to 0 and this B parameter to be 0. And this is a simple renormalization group flow diagram that clearly shows the existence of topological quantum critical point at M is equal to 0 and B is equal to 0. As you can see, the Dirac mass is a relevant parameter and B is an irrelevant parameter. Henceforth, this red point is a quantum critical point because it is infrared unstable with only one unstable direction. So what we realize that even though generically the U1 chiral symmetry is absent everywhere in this simple phase diagram, at the topological quantum critical point and at zero energy, as we approach the infrared fixed point, we recover U1 chiral symmetry generated by the famous gamma 5 matrix as an emergent phenomena. So as you can see that this was a simple example of completely non-interacting electrons, and we could already appreciate the beauty of emergent phenomena. Then you can only guess that once we incorporate the interparticle interaction or specifically electron-electron interaction, then this landscape of emergent phenomena should get much richer. And that is what I will cover for the rest of my talk. And the system that I pick, that is monolayer graphene. It is an interacting Dirac liquid on a flatland, so it perfectly fits the agenda of this program. And for the rest of the talk, I will show how emergent symmetry plays a role in the phase diagram or in the behavior of interacting Dirac liquid on a flatland. So graphene, a brief introduction. This is constituted by atom thick honeycomb lattice, which you can construct by two interpenetrating triangular sublattices given by A and B. And this is where it differs from standard square lattice, that if you go to every site and around that site center, there is a lack of inversion symmetry. That means if I come to this particular site, then if I go upward, I find a B sublattice. But if I go downward by the same distance, I do not find a B sublattice. So this is what I mean by saying that lack of inversion symmetry about site. And this is exactly what is responsible for the emergence of so-called the Dirac type of dispersion, unlike the situation what we encounter in a square lattice where we find extended Fermi surface in 2 dimensions. And if you diagonalize a simple tight binding model written on this honeycomb lattice, what you find that there are 6 such Dirac points, which are grouped into 2 categories. One category is shown by red, and another category is shown by these blue circles. But all the blue type of Dirac points, they can be connected by linear combination of Bravais lattice vector or the reciprocal lattice vector, and all the red Dirac points can also be connected by reciprocal lattice vector. So at the end of the day, we end up with only 2 inequivalent Dirac points, which we pick to be one at K and another one at minus K. And in the proximity of these two inequivalent Dirac points, the dispersion is like what we saw in our, let's say, elementary high energy physics course. The energy scales linearly with the momentum, unlike the situation in a Fermi liquid. And instead of an extended Fermi surface, we end up with Fermi points. Now, the low energy massless Dirac fermion, therefore, we need to count the degrees of freedom properly. And for now, I am not going to talk about the chemical doping. So I will throughout assume that the chemical potential that can be controlled by gate voltage is pinned at the apex of this conical dispersion or this band touching point. Then this momentum Kx and Ky, they needs to be multiplied by proper matrices. And this gamma matrices, it is composed of 4 independent set of Pauli matrices, eta, sigma, tau, and alpha. And this 4 set of Pauli matrices, alpha operates on sublattice because I have A and B sublattices, tau on valley because I have 2 inequivalent valleys, sigma on spin, and eta on Nambu. Although I did not have to introduce the notion of this Nambu doubling, but for future reference, I just decided to introduce it at the very first stage. But you can go through most of the result without at all introducing the notion of this Nambu degrees of freedom. But let's just introduce it since we eventually have to. And then we have to look into the pertinent symmetries. First of all, there is sublattice reflection symmetries that tells us if we exchange A and B sublattices, our theory must be invariant, because it does not matter, because these are all made of carbon atoms. So which one I call A sublattice, which one I call B sublattice, that should not affect my theory. Similarly, I should also have the valley reflection symmetry, which one I color by blue, which one I color by red, that should not matter. Also, I should have a 90-degree rotational symmetry. I should maintain the translational symmetry, which in the continuum limit or in the low energy limit is represented by an U1 rotation generated by this matrix, which again in this same basis, Nambu, spin, valley, and sublattice. Then of course we know that graphene in its normal state does not break time reversal symmetry. So time reversal symmetry should also be a good symmetry. And finally, since graphene is made out of carbon atom, at least to the 0th order approximation, we can completely forget about the spin orbit coupling because carbon atoms are pretty light, and claim that the spin rotational symmetry also a good symmetry. So these are the pertinent symmetries. And this is the full description of the non-interacting system. So now we want to introduce the electron interaction or the interparticle interaction. And this whole landscape of interacting Dirac fermions can be divided into 2 sectors. On one hand, we can this long range or 1 over R type of Coulomb interaction. If they are separate, then they will interact via Coulomb interaction. But not only that, give me a second. Can you still hear me?
Yes, but we had some delay. So maybe you switch off your video. Maybe that helps for the.
Yes, I can do that. Yeah. How do I do it? Give me a second. I think if I switch off video, it will be better. Yeah. So can you see my talk now, Olga?
Yeah, it's perfect.
Okay, good. So as I was saying, that the whole landscape of interacting Dirac electrons can be divided into 2 big portions. One is the long-range Coulomb interaction between charged particles, and another sector is constituted by Hubbard type of interaction or the short-range interaction. And when I say Hubbard-like interaction, I not only mean on-site Hubbard repulsion, but any finite range interaction that includes on-site, nearest neighbor, next nearest neighbor, and longer range interaction as you want to go to. But this is not the 1 over R tail. So the interaction is already chopped off after certain lattice spacing. So the role of the long-range Coulomb interaction is now fairly well understood, that the long-range Coulomb interaction, it is a marginally irrelevant perturbation if we think about interacting Dirac liquid, which only renormalizes the Fermi velocity. And this renormalization produces logarithmic enhancement of the Fermi velocity. And quite encouragingly, this logarithmic enhancement of the Fermi velocity has already been observed in experiments. And this conclusion remains completely unchanged, even if the strength of the Baer-Coulomb interaction is extremely large, which at first sight may appear a bit counterintuitive, but there has been extensive diagrammatic quantum Monte Carlo or diagrammatic Monte Carlo calculation by the group of Nikolai Prokofiev, who varied the strength of the Baer-Coulomb interaction from the value of 0.25 up to 3. And you can see in all these, for all these Baer values of the long-range Coulomb interaction, the fine structure constant shows logarithmic decay, which in turn produces logarithmic enhancement of the Fermi velocity, because fine structure constant is E square over the Fermi velocity. On the other hand, so the outcome of long-range Coulomb interaction, although it has been observed experimentally, which is quite encouraging, but it is reasonably well understood by now, and there is not really nothing new is going to come out of long-range Coulomb interaction. On the other hand, the role of the short range or the Hubbard-like interaction, at least in my personal opinion, is far more interesting, and we still need to understand this problem. But unfortunately, at least in monolayer graphene, we haven't seen any direct experimental ramification of short-range Hubbard-type interaction. But who cares? At least now extensive numerical analysis can be done, where our result can be tested in experiment that is performed on a computer. So what is in simple words, what are the roles of this short-range interaction? That unlike the long-range Coulomb interaction, the weak short-range interaction is irrelevant. That means that if there is sufficiently weak but generic short-range interaction, then Dirac liquid should be a stable state. But if the short-range interaction becomes sufficiently strong, then this interaction becomes relevant. And once the interaction becomes relevant, that is an indication of spontaneous symmetry breaking and onset of an ordered state. Now the question is that I discussed with you many different symmetries of the system, and at least some of them can be broken explicitly by the ordered state. So as a consequence, there are many possible candidates for the broken symmetry phases. The question then arises naturally, what are the best candidates for the ordered state? And if you restrict your question to 0 temperature, then as it turns out that the best candidates for the ordered state are these so-called the Dirac masses, which gets dynamically generated when the short-range interaction becomes sufficiently strong. And this phase transition is an example of quantum phase transition, because you are at 0 temperature and you are tuning a non-thermal parameter like the interaction strength. And typically this type of phase transition takes place via quantum critical point. And the Dirac masses, they spontaneously break discrete crystalline or fundamental crystalline symmetries or fundamental symmetry like the time reversal symmetry, or it can break continuous symmetry or both discrete and continuous symmetry. Now the question that we have to ask, what are the candidates for the masses? And as it turns out, there are 6 masses in the excitonic channel and 3 masses in the superconducting channel. First, we look into the masses that are insensitive to the spin degrees of freedom, such as the charge density wave that produces the staggered pattern of electronic density, maintaining the half filling condition. Quantum anomalous Hall insulator that produces intra-sublattice circulating current, which circulates in opposite direction on A and B sublattices, or Kekulé valence bond solid, which breaks the translational symmetry and it enlarges the unit cell. Now we can take these 3 excitonic orders, which are completely insensitive to the spin degrees of freedom, and construct a spin version of them. So the charge density wave, its spin version is the antiferromagnet. So instead of having staggered pattern of electronic density, now we have staggered pattern of electronic charge. Quantum spin Hall insulator, you have the circulating currents, but the circulating currents, they have opposite direction for the opposite spin projection. Similarly, you can also construct the spin version of the Kekulé valence bond solid, where the distorted bonds for the up spin and down spin, they have opposite sign. So 3 + 3, we have covered 6 masses in the excitonic channel, but that does not exhaust all the possibilities. We also have to account for the so-called Nambu masses or the superconducting masses. And as it turns out that there are 3 such candidates. One is the simple S wave, which is the on-site spin singlet Cooper pair. FOF pairing, where a spin sitting on a specific side of the honeycomb lattice can pair with the 6 next nearest neighbor site residing electrons with the same spin, but the Cooper pair changes sign 6 times. That's why we call it an FOF pairing, and it is a triplet pairing. And finally, so-called this Kekulé superconductor, which is also an example of commensurate full Farrell-Larkin-Ovchinnikov type of superconductor, which also can be classified by another name, is called the pair density wave. So in this phase, the underlying honeycomb lattice, there is no distortion, but the Cooper pairs, they pick up exactly the same pattern which I showed you for this Kekulé valence bond solid. So that's why we call it a Kekulé superconductor. So we have covered all the possible masses, and as you can see that each of them, they break distinct symmetries. So they can all be classified according to the symmetries they are breaking in the ordered state. But that does not quite complete the story yet. But you can also realize that there are certain pair of these ordered phases which can be combined together to form a much enlarged composite mass orders. Like you can take antiferromagnet and Kekulé valence bond solid and construct an SO5 order parameter. And these 5 masses, 3 for antiferromagnet and 2 for the valence bond solid, they reside on these vertices of the pentagon. And these arms, these are nothing but the chiral symmetry or the chiral rotations that is connecting different components of this SO5 mass. And all these arms, these are these generators, they commute with the Dirac Hamiltonian. So I can form an SO5 mass from antiferromagnet and valence bond solid. And you can see that there are altogether 10 arms because an SO5 group has 10 generators. Similarly, you can also put the quantum spin Hall insulator and SOF pairing and construct another enlarged mass order with SO5 symmetry. And finally, you can put 3 orders, charge density wave that is sitting on this top vertex, Kekulé valence bond solid sitting here and here, and SOF pairing sitting here and here, construct another SO5 symmetric mass order parameter. And these are the all 3 SO5 symmetric order parameter that you can construct. And you also need to appreciate that this is the largest group that you can construct out of these masses because of the dimension of the Dirac spinor in the Dirac system. And there are only 3 such candidates that are consistent with the microscopic symmetries of the system. And you can look into this beautiful paper where all the 5 tuplet of masses were tabulated, but as it turns out, only 3 of them are relevant because you want to preserve all the microscopic symmetry. Rest of these 5 tuplets, these are just some mathematical game you can play to tabulate them, but they are not consistent with the microscopic symmetries. So what we realized that Dirac fermions in graphene can support a plethora of mass type of order, both in excitonic or insulating and in superconducting states, altogether 9 of them. And not only that, we can also, there exists an internal symmetry among these competing orders like antiferromagnet and valence bond solid or quantum spin Hall insulator and SOF pairing to build a larger mass type of order parameter by exploiting the internal symmetry among or between these orders. Now the question we have to ask ourselves that what are the importance of this internal symmetry that we just discussed? Because so far I did not discuss any effect of electron-electron interaction. So the pertinent question, after we introduce ourselves with all these beautiful algebras of the internal symmetry among competing orders, that can we realize this internal symmetry among competing orders as emergent symmetry at various quantum critical points through which an interacting Dirac liquid becomes unstable toward the formation of various broken symmetry phases. And that's what I'll be discussing. So the setup is the following, that we start with the generic 4 fermion interaction here with coupling constant G, M, N. M and N, these are matrices operating on sublattice, valley, and spin indices. And once we impose all the microscopic symmetries I discussed with you, the number of coupling constant reduces dramatically to 18. But the story doesn't quite end there. You can exploit further a mathematical identity called the Fields relation and show that if you start with a theory of 18 symmetry allowed quartic interaction, you only have to deal with 9 coupling constant if we are dealing with contact type of interaction. And what we will be discussing, it is completely insensitive to which 9 coupling constants we choose, as long as they are allowed to be chosen. And then what you do, you first perform a simple scaling analysis in the presence of the short range electronic interactions. And you can immediately show that the scaling dimension of this local 4 fermion interaction is -1, because the scaling dimension is d minus z. D is the dimensionality of the system, which is 2. Z is the dynamic scaling exponent, which is 1 because it's a Dirac system.
You're
As
muted.
a result, yeah,
Okay.
I muted myself purposefully. Yeah. And
Okay.
any weak interaction is an irrelevant perturbation. So if anything has to happen driven by the short range interaction, it has to happen at intermediate or strong coupling. Therefore, we need a control parameter in order to address the emergent physics at intermediate coupling, and that we can accomplish by performing a controlled perturbative expansion about the lower critical 1 spatial dimension. Instead of staying in d is equal to 2, we say that we will approach the 2 dimension by starting from lower critical dimension 1 in terms of quote unquote the small parameter epsilon. Then the scaling dimension of the 4 fermion interaction becomes minus epsilon, and we have a small parameter in our perturbative expansion, which we will augment by standard technique of Feynman diagrams. So you start with this bare 4 fermion vertex, then you renormalize it at least to the leading order in epsilon expansion by this 1 loop diagrams. And here you can say that these black lines are the slow modes and the blue lines are the fast modes. So once you integrate out these fast modes, you get a renormalized actions in terms of the renormalized coupling constant in terms of the slow modes. And that renormalized coupling can be expressed in terms of the so-called the renormalization group flow equation. And here, one comment that needs to be made, that all the matrix algebra when you perform the loop integral needs to be done in specially d is equal to 2, and finally the shell integral is performed in d is equal to 1 plus epsilon, because the symmetries that we are discussing, or we want to see those symmetries as emergent symmetries, these are very specific to dimensionality, and namely in d is equal to 2. And once you write down these flow equations, you can look for the scale invariant fixed points in yeah, can you hear me?
Yes, you had some
Okay.
delay for a short period,
Yeah,
but
okay.
we can hear you.
Okay, so Gaussian fixed point at trivial coupling, that shows that Dirac semi-metal is a stable phase for sufficiently weak interaction. And there are 5 quantum critical points which are infrared unstable, but in only one direction. And all the quantum critical points appear at coupling constant of the order of epsilon. And there are 9 bicritical points which are also infrared unstable, but in each of them in 2 directions. And typically, the bicritical point, they separate the basin of attraction of different quantum critical points. Whereas the quantum critical points with only one infrared unstable direction and 5 of them, they control the continuous phase transition from Dirac semi-metal to various ordered phases. But what we want to understand the role of the symmetry at these quantum critical points. So what we do, so now what we have is the soup of interacting Dirac liquid which is residing at the verge of spontaneous symmetry breaking, and all possible correlation has developed, but we do not know which ordering tendency is being boosted maximally or minimally. So in order to probe this interacting Dirac liquid full of incipient order parameter fluctuation, we need to probe them with so-called the composite field associated with all the symmetry allowed order parameters or the broken symmetry, characterizing broken symmetry phases. And there are 9 singlet particle hole order, 9 spin triplet particle hole order, 5 spin singlet superconductors, and 4 spin triplet superconductors. And these are tabulated here. And then you renormalize these bare values of these composite fields in the presence of interaction. That will renormalize the composite field scaling dimension, and in turn will give us the information that which pairing or which ordering tendency is being maximally boosted when the Dirac liquid is residing at the verge of the spontaneous symmetry breaking. And once you compute these Feynman diagrams, you can also write down the flow equation for this composite field, or so-called the source terms, like this. And the quantity of our interest is the one that is sitting on the right-hand side of this flow equation. When you supply this, the values of the coupling constant by the ones which are at the quantum critical point, you get the scaling dimension of the order parameter, all of them. And the order parameter with the largest scaling dimension develops the strongest propensity toward nucleation. And I'm not going to ask you to read this table. So this is for the particle hole singlet, particle hole triplet, and we also compare the pairing channel susceptibility or the scaling dimension. So once we perform this symmetry analysis and compute the scaling dimension, we are now there to fully classify the quantum critical points. So first of all, as I said, there are 5 quantum critical points. One of them corresponds to quantum anomalous Hall insulator, transition to quantum anomalous Hall insulator, where this order has the largest scaling dimension. There is another Z2 quantum critical point with charge density wave, but the most interesting one are the quantum critical point 3, 4, and 5. Recall that the largest symmetry we could construct from all the competing masses is the SO5 symmetry for graphene. And there are exactly 3 such candidates. Now look into this quantum critical point 3, 4, and 5. All 3 candidate SO5 symmetry has been restored at quantum critical point 3, 4, and 5. Quantum critical point 3, quantum spin Hall insulator and SOF pairing constitute an SO5 vector. Quantum critical point 4, charge density wave, valence bond solid, and SOF pairing, that also constitutes an SO5 symmetry. And finally, the antiferromagnet and the Kekulé valence bond solid, that also constitute an SO5 symmetry. So what we are discussing, this internal symmetry among the competing orders, this is not just a mathematical game that we are playing. What we realize that if we treat the electron-electron interaction properly by respecting the symmetry, at the metallic quantum critical point, all this largest symmetry, they are going to get restored as emergent symmetry. So remember that there was no symmetry between charge density wave or valence bond solid when I started to coarse grain my theory. only at the scale invariant, infrared unstable quantum critical point, this symmetry between, let's say, the antiferromagnet and the valence bond solid got restored as an emergent symmetry. So a couple of comments here that this result that I just discussed with you, it does not matter how you integrate how you perform the shell integration. You can also do it in a Lorentz symmetric way. Results remain unchanged. Even you can also introduce Lorentz symmetry at the microscopic level, which is not very physical because at the end of the day, we want to go to Hubbard type of model, which does not preserve the Lorentz symmetry at the microscopic level. But at least as our game, we can introduce the Lorentz symmetry at the microscopic level. The number of quantum critical point, number of bicritical point, they are symmetries. It is a very robust outcome. So what we find that all three SO5 symmetries that are allowed in this graphene type of structure emerges at quantum critical point. But now the question is, what are their role if we look into the phase diagram of some microscopic model?
Ethan, you have 4 + 5 minutes left.
Okay, thank you. So extended Hubbard model you can write in terms of Hubbard U, nearest neighbor, next nearest neighbor interaction. These are all written at the lattice level. Now the question is that how do you go from the lattice level to the continuum level? The task is very simple, that these are fermionic densities, so which can be expressed in terms of creation and annihilation operator. And those you express in terms of the Fourier modes around 2 values. And then different microscopic model will give you different set of initial conditions for the 9 couplings that you have chosen. Then what you do, you increase the Baer strength of this microscopic coupling or couplings until at least one of the coupling diverges, it becomes infinity. And when the coupling constant diverges, that means you are leaving the paradigm of perturbative analysis, means your perturbation theory is no longer valid. And that in turn tells you that your stable nodal Dirac liquid is no longer stable. And there is an onset of ordered phase. But in order to unambiguously pin down the pattern of symmetry breaking, you also run the flow of these conjugate fields that I just discussed in the spirit of the Kalan-Simanzik equation and find out which conjugate field is diverging in the fastest way. And that determines the pattern of symmetry breaking. So these are standard tricks. But what is most important is that identifying the quantum critical point. So soon you will see there will be many different phase boundaries between Dirac semi-metal and ordered phases. But once we go at the very close vicinity of this phase boundary between Dirac semi-metal and ordered phase, if we look into the renormalization group flow of the coupling constant, it spends lots of time in the close vicinity of a quantum critical point. And you can unambiguously pin down which quantum critical point controls the phase transition to which ordered phase. So first example, I name it the Kekulé-Hubbard model. My x-axis is the microscopic Hubbard model, and y-axis, this is not really a microscopic model, but you can take it as a phenomenological model, where I show that the quartic interaction in the valence bond channel. As you see, half-filled bipartite lattice repulsive Hubbard interaction gives antiferromagnet. Attractive Hubbard interaction gives an pseudospin SU2 symmetric simultaneous nucleation of charge density wave and S wave. So at least we benchmarked our RG calculation from the theorem of Hubbard model. And when the interaction in the Kekulé channel dominates, then we find the Kekulé valence bond solid. But that is not the point. The point here I want to emphasize is that if you look into this entire phase boundary from Dirac semi-metal to antiferromagnet, Dirac semi-metal to valence bond solid, of both of these transitions, these are controlled by the SO5 symmetric quantum critical point where antiferromagnet and valence bond solid has the identical scaling dimension. Similarly, this portion of the phase diagram where you see the nucleation of valence bond solid and this pseudospin SU2 symmetric charge density wave and S wave pairing, this is controlled by another SO5 symmetric quantum critical point where charge density wave, valence bond solid and S wave pairing, they all have degenerate scaling dimension to produce another SO5 symmetric quantum critical point. So both antiferromagnet, valence bond solid transition, they are controlled by one unique quantum critical point, which has the SO5 symmetry between them. Now you can go to more microscopic model with Hubbard U V1. I'm running out of time, so I'm not going to discuss this phase diagram in details, but the same outcome remains true, that antiferromagnet transition takes place through this SO5 symmetric quantum critical point. Finally, once you introduce V2, then we clearly see existence of the topological quantum spin Hall insulator. And this transition is again controlled by another SO5 symmetric quantum critical point where spin Hall insulator and S wave has degenerate eigenvalues. So not only the quantum critical point, at the quantum critical point, the internal symmetry gets restored as emergent symmetry, but these highly symmetric quantum critical points, they also control phase transition to distinct broken symmetry phases. And we have seen the three such examples, which are the only allowed SO5 symmetric quantum critical point. Finally, how about order parameter fluctuation? You can address it from the Gross-Nouveau-Yukawa type of theory. As I'm running out of time, just wanted to mention you that even in the Gross-Nouveau-Yukawa business, where you do not perform the perturbative analysis about the upper critical dimension, but not the lower critical one spatial dimension, but about the upper critical three spatial dimension, there as well you see that, let's say this was an antiferromagnet quantum critical point, this was a valence bond solid quantum critical point. Once we incorporate the fluctuation in the competing ordered phases, these two putative quantum critical point, they get unstable toward a new quantum critical point, or you can also say this is a multi-critical point where SO5 symmetry gets restored. But this Gross-Nouveau-Yukawa type of business, it has a inbuilt drawback that you have to introduce the notion of competing orders from the outset. Whereas when we perform the RG analysis about the one spatial dimension, then we don't have to introduce any incipient fluctuation by hand. Rather, all the symmetry allowed incipient fluctuation in this strongly interacting Dirac liquid, they are all present. You just need to know how to extract that information. And once you do extract that information, you see that there exists no pure quantum critical point associated with, let's say, antiferromagnet or valence bond solid or quantum spin Hall insulator or S-wave superconductor. Whenever you can form an enlarged SO5 super mass vector order parameter, all the transition takes place through SO5 symmetric quantum critical point. And we can also support this observation from an epsilon expansion about the upper critical dimension. So to conclude, that correlated semi-metals provide the ideal platform where we can observe emergent symmetry from the internal symmetries of competing orders at scale invariant metallic critical point. For graphene, pertinence internal symmetry is SO5 symmetry, but this observation is not at all limited to relativistic fermion on flatland. As a matter of fact, Andras and me, we have already demonstrated it for three-dimensional interacting Dirac system. Furthermore, it is also nothing special about the relativistic fermion. This emergent enlarged symmetry among competing orders at metallic quantum critical point can also be seen for fermions which are not relativistic fermions, which has been shown in this paper recently. And finally, just want to say that this internal symmetry plays a crucial role when it comes to induced superconductivity once we dope away from the Dirac point. And this has been discussed by Andras in the poster session. And with that, I want to thank you for your attention, and I would love to take any question that you might have.
Yeah, thank you very much. Thanks for this inspiring talk about symmetries. Questions, please. Joseph?
Yeah, hi, Bitan. So I have a question. So in some of the Monte Carlo simulations, like Fakir simulations, it seems that they do see like the standard gross de Veur classes, right, for the semi-metal to AF, and then the XY universality class for the AF to VBS. So how should we understand that in light of your RG calculations? Because you would predict that there should be the same universality class for both transitions, right?
So you have to understand that these are metallic quantum critical points. So deep inside the ordered phase, and your fermions are completely, it tells you how to understand the quantum phase transition from the semi-metallic Dirac Dirac system to an ordered state. But some of the simulation done by Fakir, he continued to increase the strength of, let's say, the Hubbard interaction. So he's deep inside the ordered phase. So your notion of any gapless quasi-particle excitation is practically moot. And that transition should be a bosonic ordered parameter transition, unless there is some role of topological defects.
Yeah, I guess I didn't mean like the AF to VBS transitions, but just the semi-metal to AF and semi-metal to, let's say, valence bond solid. So you would predict that is the same SO5 enhanced QCP for these transitions, right? But
absolutely, absolutely.
But yeah. I thought he found gross de Veur, standard gross de Veur. Anyway, maybe Fakir can comment, but
no, the answer to your question is that if I'm approaching antiferromagnet and valence bond solid from Dirac semi-metal side, just look into this phase diagram that I'm showing on the right corner. All these transitions will be controlled by this red quantum critical point, which is the enlarged SO5 symmetry.
I see. Okay, so you're saying the vertical and the horizontal lines, both of them, they're controlled by the same red.
Yeah. Yeah. And this is supported by this RG flow diagram. So this putative quantum critical point in the pure antiferromagnet or valence bond solid, they become unstable soon as you introduce the fluctuation in the competing order channel and flows toward this higher symmetry quantum critical point. Yeah, sorry, I just cannot keep talking constantly, just this, yeah.
Thank you, you answered my question, thank you.
You're welcome.
So there's another question by Shaivish.
Yeah, I guess following up on that same question. So are you saying that as the phase transition is observed from the Dirac metal to let's say an antiferromagnet, at the transition, you also start seeing other fluctuations? So numerically should be, because typically one would have just looked at the antiferromagnet as the main fluctuating order parameter, but you're suggesting that there are other fluctuating order parameters that also become sort of important.
Yeah, they might not be the true long range order, but they could be easily be the short range order. So for instance, if you are increasing strength of Hubbard interaction, no doubt you will see antiferromagnet ordering, but it is not only the antiferromagnet order that is becoming very prominent close to the transition. One should also look into the valence bond correlation. But it might happen that this Hubbard model is so far from this SO5 symmetric quantum critical point that you will still get good quality data collapse, and if you just take the SO3 antiferromagnet quantum critical point.
So this is interesting to me, because recently we have been looking at another type of lattice model where there is of course more symmetry in the system. Oops, sorry about that. And then what we would like to understand is, because of the presence of that extra symmetry, we believe there is a new critical point which is different from that of the Hubbard model. So it would be good to, so maybe we should have a discussion about how that extra symmetry maybe is enhanced to more symmetries, and that's something we thought about. but maybe you have more insight into what's going on. Maybe if you're there for my talk, I would love to talk to you about that later on.
Yeah, sure. We can definitely talk about it.
So I see, Flakir, you have your mic open. Would you like to ask a question?
No. Hi, Vitan. I'm fine. So, well, just to confirm, so your claim is that the Gros-Neveu SO3, which we see, is actually, if we go to huge system sizes, we should flow to the SO5.
Yeah.
That's your clear claim.
Yeah.
But then we're very far, right? Because we do measure the VBS correlations and we I mean, yeah, okay. Mm-hmm. Thank you. Yeah.
Sure.
And sorry, just briefly. So in the format of epsilon expansion, this comes about when you look at these biquadratic couplings between the two competing order parameters, like phi AF squared times phi VBS squared.
That is not sufficient, because if you take pure bosonic theory, take an O3 cross O2, there is no SO5 quantum critical point in pure bosonic theory. So
No,
you
but
need
with
fermions.
With the fermions, like G and Y.
With the fermions.
Okay.
Yeah.
So you have this
Fermions
coupling.
are absolutely necessary.
Okay.
Yeah.
But you need the biquadratic coupling in the format of epsilon to see that instability of the. Okay.
Yeah, the point is that you don't have to put that biquadratic coupling by hand at the beginning. If you don't put it, it will be generated even at the one loop level.
I see.
Yeah.
Okay, thank you.
Sure.
Okay, so I see no further questions. Thanks to all speakers of this afternoon.